So one new topic that I want to talk about before the exam on Wednesday. Like I said a minute ago, this is easier than the fundamental theorem of calculus, the antiderivative construction theorem, though I do want you to know that as well from section 6.4, and we'll talk about that again as well as review more generally for the exam. And that's the idea of something called average value. And let's motivate this with an example. Let's say V of t represents your speed at time t. And you're after the distance traveled. I could call this, as I've done, speed of t instead of v of t, because v of t makes you think velocity. But again, if you're only traveling in one direction, the speed and the velocity are the same. It's only when you go back and forth that speed and velocity are different. Or if you travel in more than one dimension. We know that the distance traveled well, I could write it as a function, dist of t, we've done that, an integral from the starting time, say 0 to time t, of v of, you might call it u du. But I also could just think of a particular interval from, say, a to b, and say, what is the distance traveled over that particular interval of time? Say the speed is in meters per second. The distance traveled then would be in meters. And what would it equal? You should know this. I don't mean something simple. I mean an abstract idea here with the symbol.
The integral from a to b of.
Yep, the integral from a to b of the speed. By the way, as far as units for the integral go, it's helpful to pretend this is a multiplication, and I did hint at that before. Pretend this is v of t times dt, even though when we initially talk about integrals, it's kind of like with derivatives, the dt or dx or whatever it is just telling you what the variable is. The variable is t, we're integrating with respect to t. However, Leibniz, Leibniz was the one who introduced this notation. Leibniz did imagine this to be a multiplication, v of t times dt. dt being an infinitesimally small amount of time. Now, in the real number system, there is no such thing as an infinitesimally small amount of time. In physical reality, there theoretically could be a smallest amount of time. You know, is the nature of reality continuous or discrete? Many scientists think it's discrete, so there technically would be a smallest amount of time, but mathematically speaking, there is no such thing as an infinitesimally small number. However, in many circumstances, it doesn't hurt to pretend. And I've emphasized this before, scientists and engineers often do pretend that this is a multiplication. V of t times dt, something in meters per second times seconds. And the seconds would cancel, giving you a quantity, v of t dt, that is in meters, a tiny amount of distance traveled. And then the integral is like adding. To find the total distance traveled, add up, integral being like adding, add up the tiny distances traveled. This is a fundamental thing to realize when you're in your science classes and they're talking about applying integrals. They are thinking that way. They're not thinking about limits of Riemann sums necessarily, though maybe they know in the back of their mind they probably should. Okay? And they want you to get the idea of an integral intuitively. Add up the little distances traveled to get the total distance traveled. Anyway, that is the answer. That would be the distance traveled. But there's another way to think about this. You could say, well, couldn't I also figure out the distance traveled by taking my average speed, my average rate, and multiplying times the time elapsed? Take the average speed Average speed is what that's supposed to say there. That's a D at the end there. Times the time elapsed. Symbolically, oftentimes people represent an average with a bar above a variable, say V bar. It's a common way to represent an average symbolically. It's a little inconsistent. Some people use bars for vectors. I use little half arrows for vectors, whereas bars I use to represent averages. What's the time elapsed? Well, it's time A to time B, so it's B minus A. That's the time elapsed. But this should beg a question. What is the average speed? And essentially, the average speed is defined so that this equation is true. In other words, this equation is not something you prove. Instead, you use it to define what average speed means. Average speed is the number so that this product is the same as this integral. Said another way, average speed, V bar, is the integral divided by B minus A, or if you prefer, 1 over B minus A times the integral. And that pen's dying. 1 over B minus A times the integral.
Could you also write that as
Yep, means the same thing. And in general, the average value, not average speed, but average value of a continuous function say f of t defined on some closed interval, and I'm assuming it's also continuous on that entire interval, is, you could call it f bar. The book doesn't use this notation, but I am. F bar. F bar is not a function, F bar is a number. It's the number 1 over b minus a times the integral of the function f of t. And yes, that is the same as the integral all divided by b minus a. So this is a number, not a function. You might want to make a note about that to yourself. This is a number, not a function. It's important to be able to interpret this geometrically. And this is perhaps the hardest part about this, is knowing how to interpret this geometrically. But once you get it, it's fairly simple. It's based on the fact that this equation, which is a definition, is equivalent to, well, multiply both sides by b minus a. The equation f bar times b minus a equals the integral, which was the exact same thing I was talking about up here with the speed. And I had v bar times b minus a. But then if you graph the function f of t over the interval from a to b, doesn't matter what it looks like as long as it's nice and continuous. What are we after here? We're after a number f bar, where f bar times b minus a is equal to the integral. But if the graph of f of t is above the axis, the integral equals this area. That area equals the integral So what are we after? We're after a number, a height, if you will, f bar of a rectangle with base b minus a, whose area is the same as the area shaded under the green graph. We're after an average height of this function. What rectangle can I draw whose base goes from A to B, and whose area is the same as the area under the graph of the green function here. Sorry, my allergies are really, really bothering me. I even took allergy pills ahead of time. I think it is the allergies now, no longer a cold. Oh, it's hard to say exactly where it is. You try to eyeball it approximately. Maybe right about here. That's the value of F bar. If I make a rectangle with height equal to F bar, I'm trying to make this rectangle have area approximately equal to the area under the green graph. The red area is F bar times B minus A. Base B minus A, height F bar. F bar is defined so that the red and green areas are the same. Let's do an example. Let's find the average value of a particular function. We'll take a pretty simple function, say t squared, over the interval like from maybe 1 to 3, and try to interpret it graphically. Find the average value of f of t equals t squared over the interval t goes from 1 to 3. I'll go ahead and use interval notation for that, just to kind of get you used to it. This means t is between 1 and 3. And interpret it geometrically. As far as finding the average value goes, it's really easy. Okay, this is an easy problem. Just do that. Compute the integral, divide by b minus a. Or another word to say that is multiply by 1 over b minus a times the integral. 1 over b minus a, here a is 1, b is 3, is 1 over 3 minus 1 times the integral from 1 to 3 of t squared dt. That's 1/2 times, now use the fundamental theorem of calculus. One thing I haven't shown you yet is a little bit of notation here. It's a common thing to just go ahead and write an antiderivative here, 1/3 t cubed. And then to the right of the antiderivative, put a vertical line and put the limits of integration. And that's just shorthand notation. That means plug the top number into this function and subtract what you get when you plug in the bottom number. So this means 1/3 times 3 cubed minus 1/3 times 1 cubed. That's what that notation means. And it is standard notation. It's in the book. I just haven't mentioned it in class. So this is 1/2, 3 cubed 9 divided by 3 is 3. 3 minus 1/3. The integral's value is 3 minus 1/3, which is 8/3. But that's not the average value. The average value, I got to multiply by 1/2, is 4/3. I could try to draw a picture to interpret this geometrically. Let's get Mathematica to do it. Did I make a mistake? Oh, yeah, I computed 3 cubed wrong. I thought this average value seemed too small. Should be a 9. That should be a 26, and this should be a 13. 13/3. Like, that's just too small. 4/3 is too small. Right, 9. 3 cubes, 27 divided by 3. 9. 9 is the same as 27 over 3. Minus 1/3 is 26/3. Okay. 13/3. The average value, that's also 4 and 1/3. 4.3 repeating. Okay, let's get Mathematica to figure out this average value or interpret it. First, let's just confirm the calculation. F of t is t squared. In my writing assistant, for example, I can press one of these fraction buttons here. This one here. Oops, not there though. Okay, do it in the next line. 1 over 3 minus 1 times the integral from 1 to 3. Press the integral button. 13/3. Okay, so computing the average value is pretty easy if you can use the fundamental theorem of calculus, the one that you use to compute antiderivatives, or to compute definite integrals by finding antiderivatives. Interpreting this, you'd want to plot both the function f of t and also a horizontal line at 13/3. From 1 to 3. The area under the blue graph is supposed to be the area, same as the area under the goldish graph. Same areas. Said another way, the area between the graphs over here is the same as the area between the graphs over here. Here's another important way to think about average value, involving actually computing an average, right? If you took some statistics in the past, and even if you haven't taken statistics, you should know how to compute an average of some numbers. Just add the numbers up and divide by how many there are. Can average value of 13/3, can this be interpreted as a sum of a bunch of numbers divided by how many there are? Yeah, but you got to know how to do it, or what I'm talking about here. You have to bring in some randomness, and a lot of computer programs, spreadsheets, and including Mathematica can generate random numbers. I think it's random real. Generates random numbers in any given range in Mathematica. So if I want to generate some random reals between, say, 1 and 3, I can keep just re-entering this code, and it keeps generating random numbers between 1 and 3. If I want to generate a bunch of them, say 100 of them, I think I put a comma 100 here. Here's 100 random numbers between 1 and 3. If I enter it again, I'll get another 100 random numbers between 1 and 3. Those numbers, those 100 numbers between 1 and 3 are generated in a random way. And if you think about it, if you got enough of them, if it's truly random, they should average out to close to 2, right? Because 2 is halfway between 1 and 3. What are you saying? I'm just trying to generate numbers between 1 and 3 at the moment.
I'm saying it might. Oh, wait.
I'm calling this, say, data X data. If I compute the mean, I get close to 2. Not exactly 2, because it's random. And if I do it again, let's do it up here. If I do it again, I'm going to get something different. Do it again and get something different. But it's always pretty close to 2. You shouldn't expect to get 3. Something close to 2. Go ahead, question.
Do you know if the random root function includes 1 and 3 or not?
It may or may not, but it doesn't really matter much.
If it does, it's never going to get there.
Yeah, you're never going to get a number for the average here. The mean means average. You're never going to get a number close exactly 1 or exactly 3, and certainly not less than 1 and not bigger than 3. How is this related to the average value of the function? I can plug these data into the function. This might work, I forget. There's taking the same data, which you can't see anymore, and plugging those numbers into the function to get a bunch of numbers between not 1 and 3, but 1 and 9. One pretty close to 9 here. Why 1 and 9? Because I'm plugging them into the function. I'm plugging inputs between 1 and 3 into this function whose outputs are between 1 and 9. Call that y data. What's the mean of the y data? Close to 4.3 repeating. 13/3. Not exactly 13/3, but close. I did 10,000 data points instead of 100. That means really close to 2 for the x data and really close to 4.3 for the y data. Do it again. It'll happen again. Let's see if it does 100,000. Oh, yeah, pretty quick. So there's another way to give meaning to the idea of the average value of a function. Question?
Will this work in an open interval?
Yeah. Technically, to do the integral, you need a closed interval, but effectively, if the function is continuous on the open interval, you can effectively say the integral over the open interval is the same as the integral over the closed interval, since there's no area above individual numbers or below individual numbers. Below a function above individual numbers. Okay. I'm not going to assign any homework because, by the way, today is your last homework assignment. No more homework. Yay. But this still could show up on the exam. This basic idea with basic examples like this. I'm telling you. Yeah, it's not too hard, but if you don't think about it, I will tell you people have difficulty with it. So make sure you practice a couple times. On the video that I made, I don't think I did any problems like this. So try a few more examples on your own. Make sure you can do it. Check with your friends. Check with Mathematica. Make sure it's a function that's not too complicated so you can actually do the integral, right? We don't want to do like sine of t squared or something there. All right, let's now spend the rest of the time reviewing. I don't know if I'm going to have time to make a list of all the things to know from the different sections after class today. But you could think of this time we're going to have right now as being going over the different sections to know and sort of listing things out. Where did we end with exam 2? We ended at the end of chapter 3. We had started chapter 4 even a little bit. For exam 2, started in on the basics of critical points and optimization. You know, chapter 3 was all about taking derivatives, all the rules, product rule, chain rule, quotient rule, which you should still know, right? If you still need practice for those, it's worth practicing if you're forgetting some things. You can use a note card, but you know, you don't want your note card to be too full of stuff. And as I always say, and I'll say once again, you really want to go into the exam confident you could do well without a note card. The note card really should just be there just to make you feel less anxious. You should really know it well enough that you don't need to look at it, because it really just slows you down when you do. And people who spend too much time looking at the note card don't do as well. Okay, I hope you've experienced that by now. It's just there like for emergencies, just to help you feel calmer. And yeah, if you do need it in an emergency, yes, you can look at it, but you really should try to know the stuff well enough that you don't need it.
You like to use that card.
Yes. But again, if it's too full, then you're also just spending too much time looking for stuff instead of just knowing what to do. So exam 3 essentially starts at the beginning of chapter 4. So I don't want to just page through things here. Let's just list things out by writing it. So essentially 4.1 included the first and second derivative test. And I definitely talk about that in the review video. I'm not going to write everything down here, so you gotta listen, and I'll make some motions here and think. What was the first derivative? Both of these tests, what are they about? They're to classify critical points. Classify critical points as local maxes or mins. Or neither, though, in the neither case, well, the first derivative test can tell you more typically than the second one can. Think about it with me here, okay? Watch my hands. What are critical points? They're where the derivative is 0 or undefined technically. All of our examples, it was 0. We never really did an example where it was undefined. Think about local maxes and mins. You can, but I don't really want to emphasize that. So where is the derivative of 0? You find the derivative, set it equal to 0, solve for x. Those are your critical points. The first derivative test essentially was the one where we're making a number line and marking off the critical points. Maybe the critical points are, just to make something up here, -2 and 3 and 5. Maybe you have 3 critical points. And if you had 3 critical points, that's going to break the number line up into 1, 2, 3, 4 intervals on which to test the sign, positive or negative, of the derivative. Maybe the derivative is positive here, negative here. Maybe it doesn't change sign as the variable increases through 3. Maybe it's still negative between 0 and between 3 and 5, and then it changes to positive. Okay. I'm being a little bit not so good with my notation here. I really should be plugging numbers in to the derivative. That's implied here. Plug numbers in each of these 4 intervals into the derivative, essentially between the critical points and then to the left of the leftmost critical point and to the right of the rightmost critical point. Test the sign, and this tells you the function is increasing when x is less than -2, decreasing when x is between 2 and 3, still decreasing when x is between 3 and 5, and then increasing when x is bigger than 5. I'm implicitly assuming it's a nice function, the derivative's continuous, that kind of thing to say this. That means your graph of your function, well, it would look in this case maybe something like this. Something about like that. And that's telling you, you got a local max right there, a local min right there. When the derivative changes sign from positive to negative, as you pass through a critical point, it's got to be a local max. Local max. And if it changes sign from negative to positive as you pass through a critical point, that's got to be a local min. Top of a hill, bottom of a valley. This critical point right about there is neither a local max nor a local min. And the derivative is not changing sign. What's the second derivative test? You find the second derivative, and instead of testing the sign of the second derivative on either side of critical points, you instead plug the critical points themselves into the second derivative. This critical point, you can see nearby it's concave down. Second derivative is going to be negative at that critical point, and that's when you have a local max. Assuming, again, things are nice, the second derivative is a nice continuous function. All the examples that we do. Here for the local min, you can see it looks concave up. The second derivative is positive. So it's a little confusing if you don't think about the picture. Second derivative being negative means the critical point's a local max. Second derivative being positive means the critical point's a local min. If you don't draw the picture, you'll probably be confused and get the wrong answer. What happens here? The second derivative is going to be 0 there. Tells you no information. And once again, that's neither a local max nor a local min. There are special weird examples like x to the 4th, for example, whose graph, well, kind of looks like a parabola. And so there is a local min at 0. However, the graph is so flat near 0 that the second derivative at 0 is 0. The second derivative of this function is 12x squared. If you plug in 0 to that, you get 0. So the second derivative test tells you technically no information at 0, but it really is a local min still. The first derivative test would tell you it's a local min because the first derivative is changing sign from negative to positive. So the first derivative test is more powerful than the second derivative test. It applies to more situations. But in most situations, both can be used. In most situations. Section 4.2 is more about optimization. 4.2, more about optimization. I didn't really emphasize this a ton in class, though I did mention it, and I think I assigned a homework problem or two about it. Technically speaking, if your nice continuous function, if you're focused on optimizing it over a closed interval from A to B, you also need to check the values at the endpoints. Optimize a continuous function over a closed interval if we're after global extrema. They don't have to occur at the highest and lowest points of the graph don't have to occur at the endpoints, or excuse me, at the critical points. They could occur at the endpoints. So I mean, a real simple example is y equals x, okay? On some closed interval from A to B, there's no critical points, but this function on this interval does have a high point and a low point. The global extreme point, global maximum is at x equals b, and global minimum is at x equals a. That would be a kind of a silly example, but technically it applies. You know, more typical kinds of examples would be stranger kinds of graphs. Maybe you'd have something like this. There's a local maximum here and a local minimum here, but neither of those is a global maximum. The global maximum is at the right endpoint. The left endpoint is neither a global maximum nor global minimum. It looks like this point's the lowest. This local minimum is also a global minimum. I like to use the words local and global. If you've taken calculus before and done this kind of thing before, you may have had a teacher talk about relative and absolute. Relative being the same as a local extreme point and absolute being the same as global. I think local and global is better terminology. Also talked about in section 4.2 was some about families of functions. That's emphasized even more in section 4.4. Ultimately, they start to introduce it. 4.3 gets into practical optimization. So, you know, the most common example that we did was geometric problems, geometry, like maximize an area for a fixed perimeter, or maximize a volume for a fixed surface area, or minimize a surface area for a fixed volume, like for a cylinder. I think that's the practice problems I do on the exam is about a cylinder. For example, minimize a surface area for a fixed volume, for a given volume, for example, of a cylinder. Another example I could talk about would be for like a cone. You don't need to write the formula for the volume or surface area of a cylinder and cone. Technically, you should know the ones for the volume. Surface area for, especially for a cone, might be less clear. You may not remember that, but you really should know the volume formula is 1/3 pi r squared h there for a cone, pi r squared h for a cylinder. Surface area for a cylinder, if it's closed cylinder, is if the sum of the two areas of the top and bottom circles, 2 pi r squared. Pi r squared is the area of each circle individually. And then the surface area going around the cylinder is the circumference of the circle times the height. That's going to be 2 pi r h. Okay, I'm not going to bother writing down the surface area of a cone. I'll give that to you if you need it on the test. Then there were other kinds of problems that we did as well. One problem that comes to mind was when we had the river and we had the two stations and we wanted to minimize the total length of the pipe or figure out where to place the pumping station to minimize the total length. Though that was a pretty complicated problem as far as the algebra went, because the formula for the sum of the total lengths here was involved two square roots, and differentiating it was kind of nasty. And so, I mean, if I gave you a problem like that, I'd probably give you a lot of help to help avoid algebra mistakes. But theoretically, you should know the basic idea of how to do it. You still find the derivative, set it equal to 0, solve for the critical points. Try to minimize a total distance here by choosing this distance here, x appropriately. We did a few business examples. We talked about the ferry costs, and where you had the fuel costs and the labor costs. That was a bit tricky, and probably would need some help on that one. I give you one like that. I think we also did one. Did we do one where we were trying to maximize an angle? I think we didn't have time for that. So I think those are the main examples that we did. And then you had some homework problems where you modify things, like with the cylinder, maybe the cylinder is closed so that it includes both the top and the bottom. Maybe it's open. Maybe it's like a can that's open and you don't include the top of the cylinder as part of the surface area. And so then you'd have to modify the formula for the surface area. And this extra 2 right there would go away. No, actually the extra 2 up there would go away. You just have pi r squared, because only the bottom of the cylinder would be part of the surface area, not the top. It's like a can that's open, no top. So those would be ways you could modify it. There's also 2-dimensional versions of these problems with squares and circles and stuff, and in pictures like this. These kinds of fields. I think we did this one and saw it was best to be a circle. Maybe I'd put one like this on there where maybe it's less clear if the best answer is a circle or not. I mean, I guess it can't be, because I'm saying with this kind of picture, it's got to be a rectangle and a half circle. So there's no way that can possibly turn this to a circle like this one did in the problem we did in class. X ended up being 0, and so this ended up being a circle. We were trying to maximize the area for a given perimeter. So if I do one like this, I'd be somewhat likely to possibly put that kind of problem on there, number 23. It'd be worth practicing. Section 4.3. 4.4 was when we moved on to families of functions. Still talking about really optimization. Families of functions where there are parameters. The book did not do this, but I did, and you should feel comfortable with this. If I did like f sub a of x is, say, I don't know, x cubed plus ax squared plus x plus 1 or something. And I said, Maybe find any inflection points and how they depend on A, or maybe any critical points and how they depend on A, though the critical points, you may or may not have critical points. Let's go ahead and work through this one a little bit. You may or may not have critical points depending on what the value of A is. So A is a parameter. When you think about graphing something like this, you think of A as something fixed, like 2 or something. But what's most interesting is what happens as A changes. Do we go from having maybe no critical points to having a couple critical points? That's possible here. How would you figure it out? Well, take the derivative. There it is. Critical points for this kind of example will be where the derivative is equal to 0. So set this equal to 0 and solve for x. There's an A in there. What do? Well, the only thing you can do in this kind of situation, you can't factor it because you don't know what A is. But you could use the quadratic formula. And the answer is going to depend on A. The critical points depend on A. That's part of the point of these problems, is figuring out how the critical points depend on A. I use the quadratic formula here. The 3 is my quote unquote A in the quadratic formula, different than that A. The 2A is my B and the 1 is my C in the quadratic formula. Negative B really becomes negative 2A plus or minus B squared is going to become a 4A squared because 2A is playing the role of B in the quadratic formula. Minus 4 times A, the A is 3 times C is 1. All over 2 times A is 2 times 3. This becomes, when you simplify it, I'm going to break it into 2 fractions here. We've got negative 2A over 6. That'll be negative A over 3. Plus or minus, I'll write the 2 times 3 is 6 as 1/6 out in front. Square root, that's 4A squared minus 12. Maybe I want to factor a 4 out of that, like this. And then to simplify a little bit more, I can write the square root of 4 as square root of 2, or excuse me, as 2. And 2 divided by 6 is 1/3. So, I mean, it's tricky, you know. I wouldn't want to give you this problem without showing you right now how to do it. These are how the critical points depend on A. And what this is showing me is you're only going to get real number critical points in certain situations when the thing under the square root is not negative, right? We don't want to do imaginary numbers in this class. We sometimes do want to deal with imaginary numbers in calculus 2 and differential equations and linear algebra. But in this class, we don't want any imaginary numbers. Why would we want to deal with imaginary numbers in other classes? Because they end up being useful. That's why. But in this class, they're not so useful for us. So we don't want imaginary numbers there. For real number critical points, we require A squared minus 3 to be greater than or equal to 0. For real number critical points, not imaginary number or complex number critical points. We don't know how to deal with those. They can be dealt with in a subject called complex analysis, but that's way beyond this course. That's equivalent to A squared being greater than or equal to 3, which, if you think about it, is equivalent to A being greater than or equal to square root of 3, or A being less than or equal to negative square root of 3, if you think about it. For example, the square root of 3 is about 1.7. For example, 2 and negative 2 both satisfy this inequality. 2 squared and negative 2 squared are both 4, which is greater than or equal to 3. So we only have real number critical points in these 2 situations, and you don't have any critical points, I guess, any real critical points. No real critical points if A is between negative root 3 and positive root 3. Interesting. Does this make sense? Well, you could draw some graphs to figure it out. I mean, you could plug different numbers in for A and use your calculator. Well, let's just think about it actually here. If A's are, say, a big positive number like 10 or something, I guess in the case where A is bigger than the square root of 3, that's what we mean by big here. In this case here, okay, I'll put a greater than or equal to. What would happen? Pretend A is 10 here. What's the graph of this look like? Well, its y-intercept's going to be 1, right? F of 0 is 1. The fact that you got an x here turns out to mean is going to be enough to say the slope of the tangent line at 0 is 1, the coefficient of x. Near x equals 0, the graph looks like a line through the y-axis with a slope of 1. When x is close to 0, these other terms are really, really small. And the dominant terms are these two. It's like a tangent line approximation, actually. Near x equals 0, and it actually doesn't even depend on the value of a. But if a is really big, like 10, this would be like this part would be like a quadratic growing really rapidly as x goes further from 0. So the graph's actually got to be concave up here and growing pretty rapidly like a parabola. And then in the end, I know it's also a cubic in the end. So I know the end behavior. You're going to go to positive infinity as x goes to positive infinity, and actually negative infinity as x goes to negative infinity. So even though it grows pretty rapidly at first, it's got to come back down. I know it's got to be basically this kind of picture when a is bigger than root 3, and you've got two critical points, one right about there, one right about there. On the other hand, when a is less than or equal to negative root 3, like negative 10 or something, it's still going to look similar near 0, but it's going to be concave down instead of concave up. And evidently, it's still cubic with a leading coefficient that's positive. It's still got to have the same overall shape. It's got to look something like this with two critical points here and here when a is a big negative number. What about when a is between negative root 3 and positive root 3? That's where the case where there's no critical points. Again, near 0, it's still got to look the same because a doesn't affect these two parts. If a is, well, 0 here, if this x squared term wasn't there, there's, in a sense, no concavity near 0. It's not concave up or concave down. Well, in the end, it's still got to have the right end behavior. What's going to happen is you're going to have a picture like this. And that's why there's no critical points when a is close to 0. Graph is going to look about like that. Now, that's pretty complicated to put on the exam, okay, all that stuff. I mean, you should be able to do this part, say, and if I push you, maybe with some hints, do this part. But to quickly draw those graphs, that would take probably too long. Would I have you do anything else on a problem like this? Well, these formulas, while not too hard to figure out if you use the quadratic formula, are still pretty complicated if you're going to, if I was going to ask like for a local max or local min value, you'd have to plug these things into that function. That'd be crazy complicated. So I wouldn't do that. Not that you shouldn't be able to do that in principle, but it would be a simpler example. You got to plug critical points, places where local or global extreme values occur into their original function to find local max or maximum and minimum values. When I add the word values on top, you should know it's the second coordinate. It's the output of the function that I'm after. I haven't done that in this problem. I haven't plugged these things in there. You should always know the quadratic formula for any math class. I hope by now you don't feel like you need to put it on your note card. Maybe you still do, but and sing a song. X is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. But realize when I use that here that that a is different than the a in the quadratic formula. Don't sing during the exam, except in your mind. Quadratic formula is applicable in pretty much any math class. Oh, we skipped section 4.5, then we went on to section 4.6, related rates. The problems we did were like sliding ladder problem, sliding ladder. I think we also did like a expanding oil slick. Those are kind of like the simplest kinds of related problems you could do. There are many more that can get more complicated, and so kind of avoided those. I could see putting one involving, and we might have talked about this in class, like a cone that's getting bigger. Call it an expanding cone. We might have done that in class. Like if it's made out of sand. Oh, I think we did one with a coffee filter that was draining. But you could also do an expanding cone, say made out of sand, and you got sand coming to the top of it at a certain rate of volume with respect to time. And you're wondering maybe how fast the top of the cone is going up. How fast is the height changing with respect to time? So in related rates, the reason they're called related rates, first of all, is that everything depends on time. And we often think about rates when we're thinking about change over time. And they're related. You differentiate all the variables with respect to t, and you relate them with the equations that you get. It's kind of like implicit differentiation, but definitely not exactly the same. You need to make sure you assume the things that are changing over time do depend on time. And so you always need to think about using the chain rule when you do these problems. And you only plug the numbers in at the very end. Do not plug any numbers in until the very end. We did the lighthouse one too, where the light was rotating. And we're looking at the spot of the light. It's number 60. It's actually 4.6. 4.7 was mostly about L'Hopital's rule. And on the practice exam for the video, when I gave the problem that I went over, I gave the people a lot of help. I essentially told them, yes, this is an indeterminate form, that kind of stuff. And said, now use L'Hopital's rule. And so it's just a matter of doing it. Remember, it's not the quotient rule. You've got to differentiate the numerator and denominator individually and make a new fraction and take the limit of that new fraction. Parametric equations was section 4.8. Parametric equations and parametric curves. I do like the sample problem that I went over on the video. It's similar to an example we did in class. In fact, I think it was the exact same example we did in class. If you watch the video, where it was x equals t, y equals t squared, and the curve looked like this. And we were trying to find the distance traveled. And we had Mathematica do it because the antiderivative was kind of complicated, involving arc-cinch. But if you look at the practice problem from the old exam with the video, I have them and I worked through it just with the calculator, just trying to approximate the answer. You can use either an integration feature on the calculator, or you can do I think I had them do a right-hand sum, which does bring us into integration as well. I'll just not write down every section here. chapters 5 through 6, skipping section 6.3 about differential equations. There are a couple problems in the exam video that we didn't talk about. I wanted to include them anyway, just in case in future classes I talk about them. But I do a differential equations problem and a what I call a density function problem. We haven't done those things in our class, so you can skip over those parts of the video. But we have talked about the fundamentals of integration, definite integrals, including how to interpret them in terms of areas and more generally signed areas. Draw a quick picture here. So if your function looks, say, like this, from A to B, if it's always above the axis, the integral is the area under the curve. But if it goes both above and below the axis, and if I label this area A1, this area A2, and think of all these areas as being positive areas. Why? Because I want to. I think of all A1, A2, A3, and A4 as representing positive areas in the usual sense. The integral of the function only counts the areas positively when the graph is above the axis and counts the ones when the graph is below the axis negatively toward the value of the integral. So the value of the integral could be negative. It's A1 minus A2 plus A3 minus A4, whatever those areas happen to be. And that's an important thing to do with integrals because it allows them to be more widely applicable. With motion, back and forth motion, if you travel, say, rightward, your velocity is positive, leftward, your velocity is negative. So your velocity graph could be both above and below the axis. The integral, you want to represent displacement, change in position, which could be negative. You could end up to the left of where you started. And you want that. You want to be able to keep track of that if that happens in real life. With volume of fluid, say, going into a tank or where fluid's going in and going out, the flow rate, the net flow rate could be positive or negative. The water could be coming in faster than it's draining out, or it could be draining out faster than it's coming in. The volume itself could be going up or going down. You want to be able to keep track of that kind of thing. And so that's why it's a good thing to count areas A2 and A4 as negative toward the integral. There's also left-hand sums, right-hand sums, and trapezoid sums. I'll call it LHS, RHS, and trap to approximate values of integrals. And you should feel comfortable with all the notation with like the delta T and the TI and that kind of stuff. And also realize that the approximations get better, at least if your function's nice, get better and better as the number of rectangles gets larger and larger and goes to infinity. These are special kinds of sums of a more general type, which are called Riemann sums. You don't need to memorize the name Riemann sums. I'm just letting you know. Integrals, the theory of integrals can actually be a lot more general than we're doing, but we're just trying to get the basic idea. And the basic idea here with this kind of stuff is that as the number of rectangles gets larger and larger, as all the rectangles get skinnier and skinnier, the sum of their areas or their signed area is going to more closely approximate the value of the integral. And in the limit, as n goes to infinity, it should equal the integral. And we did a few problems like that. They were kind of complicated problems that I wouldn't fully expect you to do on the test. Does remind me, I have put problems like that on tests with help. But I don't think I did that one like that in the review video. And there's properties of integrals. properties of definite intervals. That was section 5.4, and also the fundamental theorem of calculus, section 5.3, and 6.4. The 5.3 one is the easier one, telling you how to evaluate definite integrals. That's this one. Do this when capital F prime of x always equals little f of x. That's in section 5.3. The one in section 6.4 was the harder one to understand. That's the derivative of the integral is the little f function, but use an x. If the variable is in the upper limit of the integral, as this is, that's the 6.4 one. They are actually related to each other, though it's not so clear how. You should be able to use both of these. This one, evaluate an integral. This one, to differentiate an integral. And we did an example last Friday where we had an integral, I think, of like cosine of t squared or something, and we tried to figure out the first positive critical point. I put problems like that on old exams. Section 6.1 and 6.2 are technically in here as well. 6.2 is just some formulas that are you've already memorized even before exam 2, like this one, for example, with indefinite integrals. In 6.1, we've done some problems like you found in there. That's where you're thinking about, for example, drawing graphs of capital F when you know little f, by thinking about areas like the problem we did last Friday. It's a more complicated version of it perhaps here. Here you're given the derivative, you're trying to draw the antiderivative by thinking about areas. That's what they do. This is definitely a problem worth studying. It's example 4 in section 6.1. Okay, so remember, we'll start really at 10:50 on Wednesday. I'll send you another reminder.